Yeah. Can anyone confirm if audio and the presentation is visible? Am I audible?
It's a receiver.
Sorry? Okay, thank you. So we'll start with the assignment third discussion. Okay. Yeah, okay. So question number one, it says which of the following spaces are strictly convex? Okay. So definition, first of all, of the strictly convex space. XB non-linear space. We say that X is strictly convex if F is not equals to G and norm F equals to norm G, which is not equal to 0, implies norm of F plus G by 2 should be strictly less than norm F, which is again equals to norm G. Okay, so this is the basic definition of a strictly convex vector space. There is an alternative definition also. The both are equivalent. You can try to prove that thing. Equivalently. So like here don't have any restriction on norms. Like what will be the norm of F and norm of G. But equivalently, we can say that you can just check for norm one. If that satisfies, then the definition also works. So okay. So here we want to check for these spaces, which of those are strictly convex. So what about the first one, L2? Anyone have any idea? Anyone can respond. This is kind of discussion session more than a tutorial, so we can discuss about the new ideas. And all. So basically, first of all, L2 is a inner product space. We have an inner product, so it's Hilbert space in that with that inner product. So we have something very particular to an inner product space, which is a parallelogram law. We will use that here. So let x not equal to y belongs to L2, and norm of x equals to norm y equals to 1. Okay. So what do we have is x plus y norm squared plus x minus y norm squared is 2 times norm x squared plus norm y squared. Okay, correct me if I'm wrong in this, but as far as this is the parallelogram law. Okay. So what is norm of x plus y squared is equals to 2 times this is 1, this is 1. So 2 times 2 minus norm of x minus y whole square. Correct? So I want to check for the norm x plus y. What will be norm x plus y? Implies norm of x plus y will be equals to square root of this thing 4 minus. Yes, yes. So norm x plus y whole squared will be 4 minus something. X minus y whole squared. And since norm is a non-negative quantity and x minus y is non-zero, so this quantity here is strictly positive. This will be strictly less than 4. Okay. So now x plus y squared will be strictly less than 4, which implies norm of x plus y will be strictly less than 2. Hence norm of x plus y upon 2 is strictly less than 1. Okay. So basically what I proved here is not just for L2, any inner
But
product space.
I think, sir, every Hilbert spaces are strictly convex.
Yes, yes. So this exact same proof will work for any inner product space. So L2 is strictly convex, we got. Okay. How about L1? So what do you think about L1? Anyone have an answer?
L1 दो जगह
No,
ले लो.
sir.
Yeah, tell me. Okay, so someone
Sir,
is saying no.
take E1 and E2. Its norms are one, but
Some there's
Okay.
some
So
but
norm
it doesn't
x
satisfy
equals
the
to norm
condition
y,
for strictly convex.
1, correct. And what will be norm of x plus y? 2,
Two.
right?
I mean,
Summation of 1, 1.
1 plus 1. Yeah, I get two.
Correct? Huh?
mm, exactly two.
Yeah, yeah. So this will be a counter example for the definition because norm x
Yeah,
and norm y is 1, but norm of x plus y by 2 is not strictly less than 1. Okay.
one.
So second one is not strictly convex, L1. How about C01?
C01. Oh,
Yeah. Same thing we can do. The direct
yes.
first cases it is not strictly convex. So we have to find two x and y's whose norms are 1, but
Yes. Take first function constant as one and second as x.
Then norm of f is 1
yeah. Yeah, so
and
f
norm
is
of g is
1.
also 1.
Yeah, norm
And
of
norm
f
of
is
G is also
1,
one.
norm g is also 1, correct. And f plus g, norm
But
f plus g is
is
also
norm
2.
2, yes.
Yeah. So same with same mechanism, this C01 is not strictly convex.
Yes.
We here the norm we are taking infinity norm, okay, for everyone, which is the supremum norm. So C01 is again not strictly convex. Okay. Second question says W be a subspace of a non-linear space V and F is a linear functional defined on the subspace W to R continuous linear functional. So in which of the following cases is the harmonic extension to V unique?
Sir, in case of if Hilbert space and if dense, W is dense in our, I mean, first and second should be true, I think.
Okay. Okay. So your claim is first and second should be true.
Yeah, I mean, dense, I'm sure about dense, and in case of Hilbert, and actually, I'm not sure. I mean, I'm not remembering right now the proof of this theorem, but I have read somewhere in it.
Okay. Okay. Cool.
Yeah.
So have you guys attending the course, following the course, the week third?
Yes, sir. Yes, sir. I'm following, but actually, I'm not watching all videos properly.
अक्षय
So,
बोल रहा था.
Okay. So anyone else? Okay. The first one I'll tell you
Hello?
first that why W dense implies the extension is unique. first one. So in fact, for the first option, you don't even need the non-linear space or something. Any continuous linear function, you don't even need the linear continuity. Okay. So anywhere, if W is a dense subspace of one metric space, suppose, and you have a function which is continuous on W, then it can be extended uniquely to the whole space because of the denseness and uniform continuity. Okay. That's a different theorem. You can see that theorem, but the similar lines will follow here also. The only thing here which is beneficial is linear continuity implies uniform continuity. So let F be from W to R. This is linear continuous functional. So what I'll do is I have to define a functional claim is there exists phi from V to R such that phi is continuous linear and let's say phi is unique. Okay. So this thing, existence of a continuous linear functional will be taken care by Hahn-Banach theorem, right? Hahn-Banach extension theorem. There's no need. The only thing we have to check is uniqueness here. Okay, that's what we want to check here now. Let's suppose there exist two extensions. Okay, suppose. Okay, so what I have right now is f1 minus f2. Okay, this is identically 0 on W, right? On W, this is identically 0 because both are extensions of the same function from W, correct? So the both are the f1 minus f2 is identically 0 on W. So my claim is now that f1 minus f2 should be identically 0 on the whole space since W is the dense subspace. For the moment, I call this f1 minus f2 as G. Since f1 and f2 are continuous functions, G also continuous function. So what we got is G of xn will go to G of x, correct? But what is G of xn? Because G is identically 0 on whole W. The xn is in W, so G of xn is identically 0. And a 0 sequence will converge to 0 element, hence G of x also should be 0. And this has happening for any x belongs to V because W is dense. So for any x, you get a sequence of points in W. So same thing will work for any random x belongs to V, which implies G
Yeah.
is identically 0 on vector on the whole space V. So what do you got? F1 is equals to F2.
F1 equal F2.
Yeah.
Yeah.
And the extension will be unique. Okay.
Yeah.
So for the second and third part, in one of the lectures of this week, I think third week itself, sir has mentioned a theorem. Okay. So the theorem says that the extension is unique if and only if the dual is strictly convex. Okay.
Yes, I agree.
Okay. Extension is unique. Extension
Yeah.
is dual.
So okay.
हिल्बर्ट के केस में तो अल्बर्ट ट्रू होगा है ना
Hilbert strictly convex to imply that.
हम्म
So okay, you can mute yourself if you want to talk in yourselves. then this extension, then the knock to the whole space V is unique if and only if V star, okay, is strictly convex. Okay, this is the theorem. Sir has, I guess, proved this theorem in one of the lectures of this week. So we'll use this theorem in the current question. Okay. So we want to check. Okay, first one is correct. Second one, V equals to L2. Okay. So what is the dual of L2? So maybe sir I mentioned the first week or
L2 is
second week.
itself.
L2, right? So for NEP actually, dual of LP, right, like this, LP star is LQ. Okay, where P
LQ.
and Q has the relation 1 by P plus 1 by Q is 1.
Yeah.
So for L2, dual is also L2, and I think we have just now seen that L2 is strictly convex. In fact, any Hilbert space is strictly convex. So by the current theorem, this the extension will be unique. Okay, and L1. Okay, so what will be the L1 star? It is actually L infinity.
It's L infinity.
Yeah.
Yeah.
So L1 star is L infinity. So the question is L infinity strictly convex?
इसमें bounded sequence है और extremely convex है ना. Take two bounded sequence.
नहीं होता है वो भी रुको
Example क्या लेगा?
दिखाता हूँ ये देखो AP1 AP1 ये दोनों एलिमेंट लो दोनों के नॉर्म 1 1
See, when you discuss in yourself, no, you keep in mind of turning off the earphones. I mean the
Sorry,
mic.
sir. Actually.
Yeah, yeah, it's okay. Okay. So is L infinity strictly convex? That's the question currently. So again, the same thing as you have said before. Also, you have to take two examples, X and Y.
Even.
Yeah.
this is not an strictly convex
I mean, even E2. Can we take E1 and E2?
Even if you see, you can try. See, if you take E1, E2,
दोनों में
what are the
नॉर्म
norms of those two? One, right? But if you
1
add,
1
again the norm will be one only. Norm won't be two.
Mm.
You can change a little bit,
yes,
you know. You can.
yes we can take x as a e1 plus e2 and y as an e1 minus e2
So you are taking X to be E1 plus E2.
yes
Just 1 1 0, and Y to be E1 minus E2.
1
क्या
minus 1.
क्या होगा
Okay. Yeah. So norm X is 1. Also norm Y
Norm
is
Y is
1.
1.
What is X plus Y? Yeah, yeah, you're correct. X plus Y will be 2 0 0 0.
yes
So norm X plus Y will be 2. Correct.
yes
Yeah. So by this example, straight away if the L infinity is not strictly convex, hence the space L1 cannot have a, I mean, need not have a unique extension.
मिल गया ना
This is question 2. Okay. So question number 3. Which of the following statements are true? First is there exists a non-zero continuous linear functional on the space C0 which vanishes on the space L1. Okay.
Sir, excuse me, sir. So can you repeat the theorem previously which you have applied in L1 and L2? So it is.
yes
Okay, where is that? Yeah, this one. Is it?
Yeah,
yes
theorem. Yeah.
W is subspace
Unique
continuous
has to be extension is unique. You can
sir, but it is here you mention v star but above you are taking u as a w as a subspace of u so both are same or different
What? I don't understand.
actually in the theorem you mentioned that let w be a subspace of u
W is subspace of no V. Oh, sorry. It's
be.
looking like U. It's V.
okay sorry
And F from W to is a extension. I mean, Harmonic extension is unique if and only dual of the space is strictly common.
Yes.
So
Thank you, sir.
Yeah, okay. So question number 3. So there exists a non-zero continuous linear functional on the space C0 which vanishes on the space L1 subspace. So for the first we have L1 is contained in C0. Okay, that's straight away. So we need a continuous functional, linear functional on C0 such that f restricted to L1 is identical to 0. What do you think? Initial guesses. See, for a hint, I can say you the we have done the previous question which used the denseness, right? We have shown that if a functional or is the identical to 0 on a dense subspace, then it will be identical to 0 on the whole space, right? With that, you can say something.
क्या पूछे?
अगर कोई फंक्शनल
So question number 3, option 1.
मुझे तो
So the actually what statement is saying is you need to give a functional linear functional f from C0 to R such that f restricted to L1 is identical to 0. Okay. Basically, there is one remark I should like to mention here. W is dense subspace of V, any vector space V, and F W to R, F from V to R continues. Actually, you don't need even linearity. Yeah, you don't need linearity. Okay, this is the theorem you can use here. Remark. You try to prove this theorem. Actually, we have proved this theorem before only in the current video. Kind of similar thing. You can try. So here the question is L1 dense in C0? That's the question. Okay. So the answer is yes. L1 is dense in C0. Hence, there cannot be any non-zero continuous linear functional. Okay, which vanishes on L1 but non-zero on the whole space C0. It doesn't exist. Option number 2, there exists a non-zero continuous linear functional on the space C, which vanishes on the subspace C0. Okay. Okay. So yeah, notation about notation. This C0 is basically the set of all sequences converging to 0. Okay. And C is set of all sequences which are convergent, just the convergent sequences. Okay. For second, you can give a linear function of f from C to R such that f of any element. Now, an element of the space is the sequence, right? So I'm writing it as an xn, so don't be confused. This xn is not one element, it's a representation of a sequence. Okay. F of xn is equals to limit as n going to infinity xn. Okay, this is a linear functional you can verify. And yeah, so f restricted to c naught will be what? Identical to 0, because c naught contains the sequences which converges to 0. So limit will be 0. So this will be your example. The third one is there exists a non-zero continuous linear function on C minus 1, 1 which vanishes on the subspace of all odd and continuous function. Yeah, okay. Okay, first of all, odd means what? F at minus x will be minus fx. So I can give a functional f from C minus 1, 1 such that phi of f equals to integral minus 1 to 1 fx dx. This is a linear function, continuous. So, and what can you say about the image of odd functions in this functional? Like if f is odd, then what will be the integral of f from minus 1 to 1? 0, right? Yeah. Hello?
Yes.
It will
Yeah,
be
okay.
0 I.
0.
0. Yeah. So this
Yes.
phi will be identical to 0 on the space of all odd functions, right? So that's what
Yes.
we want. There exist. This is question number third. Question number fourth. Okay, which of the following statements are true? Option number one is x belongs to L 5 by 4. There exists y belongs to L 5 such that norm y, phi norm of y is 1 and this thing holds. First of all, what do we know is for any p, okay, I mean from greater equal 1. So dual of LP is LQ, right? What that means is if you take any f belongs to LP star, there exists a y belongs to LQ such that f at x equals to summation xi yi I going from 1 to infinity. This is the dual, I mean the what do you say? Isometry between the duals of LP and LQ. This is yeah. Also here, what do we have? Norm of f is same as norm y. You know, f is operator now. Okay, this is what we know from the dual theory. So here, let your p is what, 5 by 4, right? Yeah, p is 5 by 4. So which implies q will be 5, okay, because 1 by p will be 4 by 5 plus 1 by q. This is 1. So now what I'll do is I'll define and I'll define a functional based on the x I have given. Okay. So x is given, x belongs to LP is given. So by by one of the consequences of Hornbanach extension theorem, there exists a functional f from LP such that norm of f is 1 and modulus of f at this x, this particular x, is equals to norm x. Okay, yeah. Okay, so by this remark now here, from this remark, for this f also there exists a y, LQ, well, q is fine, such that norm of f is equals to 1, which is equals to norm y, phi norm, and f at x will be equals to modulus of fx will be equals to modulus of summation modulus of xi, oh, sorry, not modulus, xi yi. But we know modulus of fx is what? Norm xp. Norm x 5 by 4 equals to modulus summation xi. Okay. Any doubt? If you have in this thing, you can ask. This is basic dual theory actually, nothing more in there. First is true, and with the exact same argument, second will also be true. Here the roles of P and Q will be changed. We'll see the third one now. X equals to, X is defined as X at Xn simply is equals to 1 minus 1 by n. Claim is, not claim, I mean to verify. Okay. First of all, what is norm x infinity? Anyone? Okay, so norm x infinity is 1 here. But the question is, does this equal to this quantity? Also maximum they are saying. Okay. Maximum means it will be attained. So the meaning of maximum is there exists a particular y such that we have to check this thing. Does there exist a y belongs to L1 such that now y1 is less equal 1 and summation xi yi modulus will be equals to norm x infinity. So this is we want to check that if there exists, does there exist a y like this? Okay. So what is, they will just carry forward this in this quantity first. What is summation modulus of xi y? This will be less equal by triangle inequality summation of modulus of xi into modulus of yi, right? But now, see, norm x infinity is 1, you know, which implies what? Xi, modulus of xi is less equal 1 for all I. And in fact, in particular, you can see here in current example, modulus of xi will be strictly less than 1 for all I. Okay, it will never attain 1. Which means you can get a j such that this yj is non-zero. Suppose you get a j such that yj is non-zero. So for that particular j, let j belongs to natural number such that yj non-zero, which implies modulus of xj yj it's strictly less than mod yj. Okay, strictly less than. So you'll just use this fact here, which implies modulus of summation xi yi is strictly less than mod yj and the rest of the quantity as it is modulus of xi yi I not equal to j. Okay. So what happened here is in fact this now mod xi yi, right? Xi mod xi less equal 1 for every I. Hence this quantity will also less equal mod yi for every I. Okay. So from here you get this is less equal mod yj plus summation mod yi not equals to j. But what is this? This is simply one norm of y, okay, which is less equal 1. So ultimately you got modulus of summation xi yi is strictly less than 1. Okay, but what is norm x infinity? Which is equals to 1. So this cannot happen for any y. Okay, okay. So what we have proved is for any y, modulus of summation xi yi should be strictly less than 1. Hence, the maximum of any maximum will not be equals to norm x infinity for any y. Okay, but you can say something more. You can say the supremum. If you replace the maximum by supremum, then the equality holds. Okay. So claim is norm x infinity equals to supremum over all y belongs to L1, norm y less equal 1, plus of summation x and y. Okay, try this thing. Basically, you can just take in place of y one by one ei's. Okay, the component wise sequences ei's. So for every I, we get this quantity to be just xi. So supremum over xi, which is same as norm x infinity here. So it will be same. Okay, so here the option number third is wrong. We will go to question number 5. Let V be the Banach space and J is the canonical embedding from V to V star star. Let B to B and B star star denote the closed unit balls in V and V star star respectively. Which of the following statements are true? Okay. So canonical mapping, the revision is J will be from V to V star star defined by Jx. Jx will be now linear functional. Yeah, sure, I'll share this video. Yeah, so Jx will be a linear functional on V star. Okay, so Jx at F will be equals to Fx. This is how it's defined. This is the canonical mapping. Okay, so because of the isometry, this canonical mapping is also an isometry. Okay, isometry means norm of x will be same as norm of Jx. Okay, so if you take uh, let any x belongs to B, the closed unit ball of V, then norm of x will be what? Less equal 1. But which implies norm of Jx will also be less equal 1 because it is same as norm x. Hence, J of B is always contained in B star star. Okay, but the reverse inequality is not all the time true. Actually, the reverse inequality is true if and only if the space is reflexive. Okay, so this is wrong. Next thing, if JB is dense in B star star, then V is reflexive. Okay, so quickly you can say something now. The answer of this question. Just try to think something. J is an isometry, so it will send a closed set to closed set, right? Already I told you that J of B is contained in B star star. So what can you say now? Can anyone tell me any quick answer? Is this true or not true? See, J of B is a closed set which is contained in B star star and it is dense also. Okay, this statement is true because J of B is closed and dense in B star star, which implies J of B, which is equals to J of B bar since it is closed, but which is equals to B star star since it is dense. But this implies space is reflexive. Why? Reflexive means what? This canonical mapping J should be J has to be onto, right? That is the meaning of a reflexive mapping. Yeah, that is the meaning of the space being reflexive. That the canonical embedding is onto. Okay. Yeah. So what do you have is J of B equals to B star star. From this, the claim is V is reflexive. Let any F, sorry, phi belongs to V star star. Okay. Hmm. So consider phi hat to be phi upon norm phi, which is non-zero amplitude. So now this phi hat is belongs to B star star, correct? Which implies there exists some x belongs to cap V such that Jx is same as phi hat because JB is same as B star star, right? Not just V, sorry, X belongs to B. Okay, there is X belongs to B such that Jx equals to phi hat. Hmm. Okay, so now what will be norm phi into Jx? This is equals to norm phi into phi hat, which is equals to phi. That's all. So, and norm phi into Jx is simply J of norm phi x. Okay, so for any element phi, you got a pre-image. Okay, this is J of, so for any element phi, you get a pre-image in a V such that J of x is that phi, which implies spatial reflection. Okay, yeah, now this is true. If V is reflexive, then J of B equals to B star star because of isometry. That's nothing now. Okay, so which of the following
Sir,
state?
can you please share this PDF with,
Yeah, I'll
with
share.
us? Okay, thank
Thank
you.
you.
This current PDF you're talking, right, which we are explaining now.
Yes, yes, this current.
Yeah, I'll share this now. Okay, so anyone have any doubt in this question, the reflexive part?
No, sir.
Next question. So which of the following statements are true? V equals to CCR,
Sir, I
supernorm.
have some doubts in some criteria of reflexivity.
Okay.
Like, can I ask here?
Okay, I can ask after the session maybe. We'll finish the whole
Okay,
questions,
okay.
then you can ask. Okay.
Okay.
So question number 6. Which of the following statements are true? So let V equals to CC over R, which is the space of all functions with compact support. Then the set H is set of all f belongs to V such that integral minus infinity to infinity ft dt is 1 is a closed hyperplane. So hyperplane, first of all, what is a hyperplane? So basically it is cosets of an hyperspace. You can imagine it like that. So hyperspace is a space which if you increase in one dimension, it will be the whole space. Okay, so I mean that's just a crude way to say it.
Okay.
V being nonlinear space, the subspace W is called hyperspace if a proper subspace, of course. If you take Z belongs to V minus W, then V will be equals to W direct sum span Z. Okay, this is one definition. Other definition is simply the W should has to be the null space of a linear function. Okay, since you know the for a linear functional, what will be its rank? If you take a non-zero linear functional, then its rank will be one, right? Because it goes in reals. So the by just thinking, you can see that the nullity rank nullity theorem, what has to be the dimension of null space, just one less than the dimension of whole space, right? Because rank is of one dimension. So prove this thing. W is hyperspace if W equals to null space of F for some F from V. Just a remark. Now, what is a hyperplane? Hyperplane is cosets of the hyperspace. Simply, like if we take any, okay, or instead of that definition, see, null space means what? For this, if f is a linear functional, null space means W is equals to F inverse of 0, right? So hyperplane, I call it H, will be just F inverse of K for any K belongs to R. That's all. Just kind of translations of hyperspace. That's all. So these are the hyperplanes. Okay. So our question, we have H to be this. So just by looking at the set, you can think of defining a linear functional from V to R as phi, suppose. As phi of f equals to integral from minus infinity to infinity ft dt. Okay, this is a linear functional now. So the set H is what? Just f inverse of singleton V, right? Correct? The set H is just f inverse of singleton V. But the actual question is about closeness. Hyperplane is fine. You can just see from the definition that now this H is a hyperspace, hyperplane. But is it closed? Actually, it's not. There is a theorem also. Did sir uh, mention this theorem in the lecture video that a linear functional is continuous if and only if its null space is closed? Yeah, hello. This theorem is very critical. We'll use this theorem here. So since this linear function of phi we have defined here, okay. So if the null space is closed, which implies the hyperspace will be closed, hence every translation, hence every hyperplane will be closed, right? So we'll check if the null space of this phi is closed or not. So is it fine? Like with this theorem, sir has explained this theorem in the class or not? Okay, I'll just give the proof. Maybe we'll discuss about the other option later.
Sir, theorem is clear, but what about if f is continuous? Then what can we say about image of that, image space of that?
If f is continuous, then you want to say about image, huh?
Yeah, is it closed or not?
So if f is continuous, non-zero, the image will be whole range space, right? It's just one-dimensional space in the codomain. It will be closed in the some whole space, no R.
Okay,
Yeah. The possibilities of image are only singleton zero or the whole space R. So both are closed always.
okay.
The only thing you have to worry about is the null space. Since you don't know about the V, what can be the null space, you don't know. Okay. So we'll check if the f is continuous, because if f becomes continuous, then null space will be closed, hence every hyperplane will be closed. Okay. So question is f continuous? Not f, sorry, phi we have mentioned it. Phi which is given from V to R as phi f. So since it's a linear functional, we can uh, go with the linear conditions of continuity, which is norm of, sorry, not norm, modulus of phi f has to be less equal some c times norm f, right? This should happen. This should happen for all f. I mean, there should exist a c. If at all f is continuous, then if at all phi is continuous, then there should exist a c such that modulus of phi f is less equal c times norm f infinity for all f. Okay, but let's see if there exists. So what you can try is think of think about the functions like this. Minus n to n, you put a constant 1, then maybe you just degrade it to linearly till down, maybe minus n minus 1 to n plus 1, and furtherwards it's 0, identically 0. Consider these functions fn. So what is norm fn? Yeah. So norm fn infinity is 1 here for every n. Okay. But if you consider modulus of phi of fn, this is area, right? You can see from minus infinity to infinity you are integrating the function fn's, but anyway from this left to this and right to this function is 0 only. So you'll just integrate from here to here, and if the function is positive, so the integral will be just area under the curve and restricted. So area, this will be anyway greater or equal this area because you're calculating the whole area, and the whole area will be greater or equal this small area, and the small area is what? This is 2n, this is 1, so just 2n, right? What you have is 2 times n is less equal modulus of phi fn is less equal c times norm f infinity. Sorry, fn infinity, which is 1. Let's see. So does there exist a constant c such that this happen? This should happen for all n. No, this is a contradiction because this 2n will go to infinity as n goes to infinity. So there cannot exist a c such that this modulus of phi f is less equal c times norm f infinity for all f, which implies phi is not continuous, which implies null space is not closed, which implies no hyperplane is closed. No hyperplane is with respect to this functional f inverse of singleton. This is wrong. So any doubt in this procedure I did these functionals? Yeah, I guess it's okay. We'll go to the next one. Let x belongs to L4. They have defined H now. The same thing. Asked whether it's a hyperplane or not. See, by seeing at this H also, you can think of a linear function. Right? What it is? F from L4 by 3 to R given by F at Y equals to summation xi yi can from 1 to infinity. See here x is fixed. X is fixed from L4. Okay. Why we are fixing x from L4? Because this has to be well defined, right? This Fy has to be well defined. This series should converge, and it will converge because of the Holder's inequality. What is that? Modulus of f at phi, which is modulus of summation xi yi, is less equal norm x 4 into norm y 5 by 4 by pq rule. From this, because y belongs to L4, what is it? Sorry, 4 by 3. Because y belongs to L4 by 3, x belongs to L4, hence this both quantities here are finite, hence f is well defined. Also from here only you can say that f is a continuous linear function, right? Because mod fy is less equal this sum c times norm y for every y belongs to the space. Hence f is continuous. So this h is nothing but this f inverse of singleton one again. So a hyperplane and also closed. Second is correct. Third one, v equals to c01 and if g belongs to v, they have defined same h. Okay, the exact same mechanism as of 2. You find phi from v to r, phi of f to be integral minus 1 to 1 gt ft dt. Right? Yeah, so you can verify this is a continuous linear functional and okay, what norm? We'll know. Okay, we will take supremum now. So the h given is just phi inverse of singleton 1. So we'll just check if the phi function, this phi functional is continuous. What is the modulus of phi? Is less equal norm g infinity. I mean this, sorry, here inside it's not. So I can take norm g infinity outside and the remaining part will be the one norm of f. Correct? Yeah. So this phi will be a continuous linear functional. Here we'll take v to be one norm. Okay, v to be the set of all continuous functions from 0, 1 with respect to the one norm. Okay. So what we have proved now is phi, this linear functional is continuous, hence the h will be a closed hyperplane. Question number 7. C to be the open ball with center at origin radius r. The Minkowski functional of C is given by. Okay. So the Minkowski functional is defined like this: P of x equals to infimum of set of all beta suppose positive such that x by beta belongs to C. Like for any set C, we define the Minkowski function like this. So here our set C is ball centered at 0 with radius r. Okay. So which one among these three is the correct option? We have to check. So if I take any beta belongs to this set, okay, I'll call this set to be maybe mx. This is just the notation of this set. Let's take any x in, so any beta belongs to mx. What do you have? X by beta belongs to C, which means norm of x by beta is strictly less than R, which means norm of x upon R is strictly less than beta. Okay. So for any beta belongs to mx, norm x by R is strictly less than beta. This implies infimum also is strictly greater. We are taking the infimum over all such betas. Okay. So this we have now. Norm x by R is less equal p of x. Okay. We want to show it's equal. Suppose take any m which is strictly greater than norm x by R. The claim is m itself belongs to mx, which implies m to be okay. That's fine. If this happens, then we are done, right? Because any number greater than this quantity norm x by R is already in the set, so it cannot be an infimum. This is a lower bound norm x by R. Okay. So claim m belongs to mx. So what is x by m? Norm of x by m equals to norm x by m. So this norm x by m is strictly less than R from this inequality. So done, which implies x by m belongs to C. Done. Which implies infimum of all such betas positive such that x by beta belongs to ball centered at 0, radius r, which just equals to norm x by r. Okay, this was a quick proof. Anyone have any doubt in this? Okay, we'll go to the next question. Question number 8. So A is the set points on this curve. This curve. So option number A says the set A and the y-axis, positive y-axis, can be strictly separated by a line in the plane. So what are your initial guesses? Can we separate these two curves? This curve basically and this. So option number 1 says, can we separate these two curves by means of a straight line? What can you say? Anyone? Say Himanshu?
Yes, yes, sir.
Yeah, can we separate these two curves by means of a
Yes,
straight
yes. By
line?
using Han-Banach separation theorem, we can separate this.
No. How?
Sir, Harmanak theorem says that if even any two are two convex subspaces and one of them is open, then there exists a functional which separates both of them.
Okay, so if one of them are open, then you are saying you can separate these two lines.
Yeah, and
So,
this can, I mean, this can be hold for any arbitrary number of convex sets.
so is it open, any one of those?
Yes, yes, one should be open.
Which,
Yes.
no, no, in current examples, is any one of those two open?
Oh, I think
ये ओपन कैसे है भाई ये नहीं
no. Sorry, sir, I am not getting.
No, see, you are applying the Hornbrook extension theorem, right? Here.
Yes.
So conditions on Hornbrook theorem is the two sets which you are taking should be one of those two should be open. So are those conditions met here? I'm asking. Actually, here no one is open. Both the curves are non-open, and okay. And the basic fact is, if you just ignore all the theorems and all, what I'm asking you is this is one curve, this is one curve, this is one curve. Okay. Can you make a line in between those curves which will not intersect in any of the curves? Like one curve will be the left of the line, one curve will be the right of that line. Is it possible? No, right? See, this line goes straight infinitely many, and this will go near and near as it goes up. It won't touch at all, but it will be near only at till the end. Okay, so distance, in fact, distance between those two curves is zero. That is not a factor here, but I'm saying that there cannot be a line which separates these two curves. From the graph, uh, asking you to imagine this thing, that can there exist a line between these two curves which will separate these two curves? Will prove theoretically. Okay. So suppose so according to Hanbanach extension separation theorem, what do we have is, if suppose there exists a line separation, then there exists what do you say, linear functional, right? There exists a linear functional f from R2 to R such that, yeah, and T also such that f at x less equal t less equal f at y. This is happening for all x belongs to W1 and y belongs to W2, suppose. And what is this W1, W2? This is W1, this is W2, right? This should happen from the Harmonic separation theorem, right? If at all there exists a line which separates these two curves, then this should happen. So I will contradict that this cannot happen at all. Okay, not less equal, one has to be strictly less than. Yeah, this should be the case. Okay, so W1 will be the set of all 0, comma y, where y greater or equal 0. W2 is the set of all points x, comma y, so that x greater or equal 0, y greater or equal 0, and xy greater or equal 1. So any linear functional, first of all, if f is a linear functional from R2 to R, That means there exists some element, I'll call it x naught comma y naught belongs to R2 by representation theorem such that f at any point x comma y is simply x naught x naught plus y naught, correct? It's a just representation theorem. Okay, so for any, suppose now let a point x1 y1 belongs to w1, which implies simply x1 is 0 there. So what is f at 0 comma y1 is y1 times y naught. Yeah, so I'll name this equation as equation star. So from star, y1 y naught will be strictly less than t for all y1 greater or equal 0. From this we can say that this will imply y naught has to be less equal 0, because if not, then we can find by Archimedean property we can find a y1 such that y1 y naught will be strictly greater than t, because t is a fixed real number, right? So y naught has to be less equal 0. That's the first thing. Now you look at the second inequality here. T is less equals fy for all y belongs to y2, which means that element x2 comma y2 belongs to w2. Since what is f at x2 y2? Is x2 x naught plus y2 y naught. Okay, and from star, t is less equal this x2 x naught plus y2 y naught. Okay, yeah. So first of all, t has to be greater or equal 0, because see from here y1 y naught is should be strictly less than t for all y1 greater or equal 0. So if you put y1 equals to 0, what do you get? 0 is strictly less than t, right? So t has to be strictly positive, which means x2, this, sorry, not x2, x naught. Yeah. So what can be the condition on x naught? Hmm. Yeah. So x naught also, yeah, x naught also has to be greater or equal 0, because if not, then like if x naught less equal 0, which implies x2 x naught plus again y2 y naught, this will also be less equal 0, because x2 and y2 are positive, x naught and y naught both will be less equal 0. Hence the whole this equality whole equation will be less equal 0, but this will imply that t is also less equal 0, which is not possible, because we already found t has to be strictly positive. So x naught also less greater equal 0. So we got that x naught is greater equal 0, but from Archimedean property, there exists some x2 belongs to R, I mean greater equal 0, such that x2 x naught will be strictly less than t. And this implies x2 x naught plus x2 y naught will be less than t. But this is a contradiction, since t is less equal this quantity for all x2. So we are wrong. We cannot find a t such that, no, we cannot find a t and a functional f such that this star happens. Okay, which implies these lines, these two curves cannot be separated. Okay, a little bit complicated proof, but if you observe it carefully, it's not complicated. We are just finding the conditions of x naught and y naught and then contradicting that these conditions cannot be met. Okay, yeah, so question number 8, part B. The set A, the same set, and circle of radius 1 by root 2. Okay, so here you can see straight away, like any line, if you pass through this gap, that line will separate these two curves. So there's nothing much to tell here. Any line will do the thing. Okay, I'll leave this as an exercise to prove this. Now, option number C. Yeah. So actually here the same curves. I mean, one in the upper first quadrant, other one is in the fourth quadrant. These two curves. See now graph from graph only you can see the x-axis separates these two graphs. Also you can draw the line y equal to minus x maybe. This see this line separates these two curves. Okay. So option number C is also correct. Okay, so this question number 9 actually I have some doubt. So this I'll discuss maybe in the next session. We'll go on to question number 10. If V be a Banach space and phi be a V-valued continuous mapping, which of the following statements are true? Okay, so phi is function from C01 to B continuous. So what do you know from basic metric spaces, that a continuous function from a compact space is uniformly continuous, right? Which implies phi is uniformly continuous. So since phi is uniformly continuous, there exists a delta positive such that whenever modulus of x minus y is strictly less than delta, which implies modulus of, not modulus, a norm of phi x minus phi y will be strictly less than epsilon. Okay, this is the definition of uniform continuity. We will use that here. Okay, so what is 1 by h times integral t to t plus h phi s ds minus phi t? Okay, this is equal to 1 by h times integral t to t plus h phi of s minus phi of t dt. Okay, since phi of t is just a constant for the moment, I can take it inside and h will be outside to cancel out the integrand. Okay, so if I now take the modulus, this will be less equal 1 by h 1 by mod h times integral t to t plus h modulus of modulus phi s minus dt. Okay, so if modulus of h is strictly less than delta, then s will belong to anyway this interval t to t plus h. Hence, which implies modulus of s minus t will also be strictly less than delta, which implies modulus of 1 by h times integral t to t plus h phi of s ds minus phi of t is strictly less than epsilon. Okay, because this quantity will be strictly less than epsilon times h, and divided by, yeah, h is positive anyways, so this means limit as h going to 0 integral from t to t plus h phi of s ds is equals to phi of t. Okay, so what are the options we have? Exist and equal to 0, no. The above limit exists and equal to phi of t, correct? Limit min of exist wrong. So we are finished here.